Hello and welcome. Today we're going to pull back the curtain on what feels like a kind of statistical magic. We're going to start with a really simple idea, just grabbing a small group out of a big one, and by the end we'll have built our way up to a theorem so powerful it lets us understand the behavior of millions just by looking at a tiny, tiny fraction of them. So here's the game plan for our journey today. First, we'll tackle the big why. Why do we even bother with sampling in the first place? Then we'll get into the nitty-gritty of how to do it right. After that, things get really interesting. We'll uncover a hidden pattern that shows up when you sample, and that discovery leads us straight to the main event, the central limit theorem. And finally, we'll roll up our sleeves and put this amazing tool to work on a real problem. So let's dive right in.
All right, let's start with the basic problem we're all trying to solve. We want to know things about really, really big groups. I'm talking about all the voters in a country, every smartphone manufactured in a year, or all the red blood cells in a person's body. Now, trying to study every single member of a group that large is, well, it's usually just not possible. And that's exactly where sampling comes to the rescue. It's the art and science of learning about the whole just by looking at a small, carefully chosen part.
Now, this is a question that I think everybody asks at some point, and it's a good one. It feels completely counterintuitive. How on earth can a tiny little group of, say, 1,000 people tell you anything reliable about a whole country of 300 million? It sounds like a trip, right? But it's not. The answer lies in something called inferential statistics, which is this incredible field dedicated to making smart, reliable conclusions about the whole based on evidence from a small piece. To really get this, we need to be super clear on two words. First, you've got the population. Now, in statistics, this doesn't just mean people. It means the entire, complete set of whatever it is you're interested in. It's all the likely voters. It's all the parts that came off the assembly line today. Then you have the sample, and the sample is just what it sounds like, a smaller piece, a subset that you pull from that big population. We take the 1,000 voters for the interview, we select a few parts for testing. The whole game is this. We study the sample, which is manageable, to learn about the population, which is not. So why not just go for it and study everyone? That's called a census, and it seems like it would be the most accurate, right? Well, maybe, but there are some huge reasons why we usually don't. First, the obvious ones, time and money. A full census of a country can take years and cost billions, but it gets more interesting. Sometimes it's just plain impossible. Think about a company that makes light bulbs. If they want to test the lifespan of their bulbs, they can't burn every single one until it dies. They'd have none left to sell. That's called destructive testing, and you have to sample. And here's the kicker. A really well-designed sample can often give you results that are just as accurate, if not more so, than a messy, complicated census. And that phrase right there, well-designed, is everything. This brings us to a crucial point. How you choose your sample is arguably the most important decision you'll make. It's the difference between a scientific poll that can predict an election and just, asking your family who they're voting for. The method you use determines whether you get a clear picture of reality or a funhouse mirror version that's totally distorted by bias. So really, you have two paths you can go down here. There's non-random sampling, where you might pick people because they're easy to reach or because you think they're typical. The problem is, this is an open invitation for bias to creep in and ruin your results. But then you have the gold standard, the method that all of inferential statistics is built on, and that's random sampling. The principle is so simple, but it's incredibly powerful. It just means that every single item in your population has the exact same chance of being chosen. It's like a perfectly fair lottery. By letting pure chance make the decision, you remove human bias from the selection process. It's the only way to get a sample we can truly trust. Okay, so we're all in on random sampling, but how do we actually do it in the real world? It's not always as easy as just pulling names out of a giant hat. Statisticians have developed a whole toolkit of different methods, each one designed as a specific tool for a specific job. Let's open up that toolkit and look at 4 of the most important ones. So the first tool is the purest and most basic form. It's called simple random sampling. This really is the drawing names from a hat method. The process is exactly what you see here. First, you need a list of every single member of the population, and you give each one a unique number. Then, you use some kind of pure chance mechanism. A random number generator on a computer is perfect to pick your numbers. And that's it. Whichever numbers pop up, the corresponding members become your sample. No judgment, no convenience, just pure, unadulterated chance. Now let's look at a more sophisticated tool. This is stratified random sampling. You use this when you know ahead of time that your population is made up of distinct subgroups, and you want to make sure you get representation from all of them. So in our example with radio listeners, you might know that musical taste varies a lot by age. So what do? You first slice up your population into these groups, which we call strata. Then, and this is the key part, you perform a simple random sample inside each group. This guarantees that your final sample will have the right proportions of people from each age bracket, which can make your estimate way more precise.
Okay, next up is a really neat and efficient one called systematic random sampling. This is perfect when you have a long list of things like customer records or purchase orders. Here's how it works. First, you decide on your sampling interval, which we call K. You just divide the total population size, N, by the sample size you want, N. So in our case, 10,000 divided by 50 gives us a K of 200. Then you just randomly pick a starting point somewhere in that first block of 200 items. Let's say we randomly land on number 45. From there, the rest is automatic. You just take every 200th item, the 45th, the 245th, the 445th, and so on. It's a really simple, clean system that gives you a nice, spread-out sample.
And our last tool is cluster sampling. Now, this is super useful when your population is spread out all over the place, and it would be a nightmare to try and sample individuals directly. Think about surveying students across an entire country. Instead of a list of every student, you could use cities or school districts as your clusters. The idea is that each cluster is like a mini, mixed-up version of the whole country. So what you do is randomly select a handful of clusters, and then you go in and survey every single person within those chosen clusters. It's incredibly practical, but you do have to be careful that the people inside your clusters aren't too much alike, or it can be a bit less accurate. All right, so we know why we sample, and we've got our toolkit for how to do it randomly. Now we're going to take a bit of a turn. We're about to step into a slightly more abstract world, but trust me, this is where things get really, really cool. We're no longer thinking about just taking one sample. We're going to ask a new question. What if we could take every single possible sample of a certain size, calculate the mean for each one, and then look at the pattern of all of those means? To get our heads around this, let's forget about 300 million people for a minute. Let's use a tiny little toy population. We have just 4 people, and their ages are 18, 20, 22, and 24. This population is so small we can know everything about it. For instance, we can easily calculate the true population mean, what we call mu. Just add them up, that's 84, and divide by 4. The true population mean is exactly 21. Okay, remember that number. Now, let's imagine we're going to draw samples of size 2 from this population, and we'll do it with replacement, which just means we could pick the same person twice. This table here shows literally every single possible outcome. You could draw the 18-year-old twice, giving you a sample mean of 18. You could get an 18 and a 20 for a sample mean of 19, or a 24 and a 22 for a sample mean of 23. You can see there are 16 possible unique samples we could get, and for each one, we've calculated its mean, which we call X bar. So now for the big reveal. Let's take all those 16 sample means we just saw and organize them. Let's just count how many times each value showed up. A sample mean of 18, that only happened one way. A mean of 19, that happened twice. But look what's happening in the middle. The sample means are all piling up right around 21, which, remember, was our true population mean. Our original population of 4 ages was perfectly flat, totally uniform. But the distribution of the means of our samples, well, look at that. It's starting to form a beautiful, symmetric, bell-like shape. This is not an accident. This is a clue to something incredibly profound. What we just witnessed with our tiny population of 4 is a glimpse of what might be the single most important, most powerful idea in all of statistics. It is the absolute bedrock of how we make inferences. It's the reason a poll of 1,000 people can work. This amazing phenomenon is called the central limit theorem, or the CLT for short. It really is like a superpower. And here it is in all its glory. Let's really break this down. It says, as your sample size, your N, gets big enough, the distribution of all the possible sample means will look like a normal bell-shaped curve. And here's the absolutely stunning part, regardless of the shape of the population. It doesn't matter if your original population is skewed to the right or has 2 humps or looks like a random squiggle. If you take big enough samples, the means of those samples will always form a nice, predictable bell curve. This is a fundamental truth about how numbers and randomness work. This is the magic right here. On the left, you have your parent population. It could look like anything. Most of the time in the real world, we actually have no idea what its true shape is. But the central limit theorem gives us an incredible gift. It tells us that the thing on the right, the distribution of the sample means, is something we do know. We know it will be normal. And because we know so much about the properties of the normal distribution, we can use it to do some amazing calculations. And the CLT gets even better. It doesn't just give us a shape. It gives us two beautifully precise formulas. Let's really dig into these. The first one says that the mean of the sampling distribution, mu sub x bar, is exactly equal to the true population mean, mu. This is huge. It means our sample mean is an unbiased estimator. It's not systematically too high or too low. On average, it hits the bullseye. Now, the second formula. This one defines the standard deviation of all those sample means, which we give a special name, the standard error. And it says that the standard error equals the population standard deviation, sigma, divided by the square root of the sample size n. Look at that formula. N is in the denominator. That means as your sample size gets bigger, the standard error gets smaller. The sample means get squeezed more tightly around the true population mean. This is the mathematical reason why larger samples give you more precision. It's right there in the math. Okay, that's a whole lot of theory, I know. But the beauty of the CLT is not just that it's an elegant idea, it's an incredibly practical tool. So let's stop talking about what's possible in theory and actually use it. We're going to walk through a concrete example to see how the central limit theorem lets us answer a real question and calculate an actual probability. So here's our problem. Imagine a population where the true mean, mu, is 8 and the standard deviation, sigma, is 3. We take a random sample of 36. The question is, what's the probability that the mean of our sample will fall somewhere between 7.8 and 8.2? First, we calculate the standard error, our new yardstick. It's sigma divided by the square root of n, so that's 3 divided by the square root of 36, which is 6, so our standard error is 0.5. Next, we have to translate our boundaries into the universal language of the normal curve, and we do that by calculating a z-score. The formula is just our value minus the center divided by our new yardstick. So for 7.8, we get 7.8 minus 8 divided by 0.5, which is negative 0.4. For 8.2, it's 8.2 minus 8 divided by 0.5, which is positive 0.4. Now that we have these z-scores, we're set up to find the probability. And using a standard z-table or a calculator to find the area between those z-scores, we get our answer, 0.3830. So what does that mean? It means there is a 38.3% chance that when we take our sample of 36, the mean we calculate will be somewhere between 7.8 and 8.2. Let that sink in. We started with a population we didn't even know its shape. And thanks to the CLT, we just calculated a precise probability about a future sample. That's incredible. So that's our journey from the simple idea of sampling to the profound power of the central limit theorem. It's this amazing bridge that lets us take a small, tangible piece of data that we can actually collect and use it to understand a vast, unreachable world. And it leaves you with a pretty amazing thought to chew on. If a pattern this beautiful and powerful was just hiding inside of simple averages, what other incredible hidden rules are out there governing the way our world works, just waiting for us to find them? Thanks so much for joining me.